So hello, we're Team Vortex, and this is our final presentation where we're going to cover how well we succeeded in terms of the primary and secondary mission, as well as what we can expect to do going forward and maybe improve on as well, obviously. Okay, so if we start on the ground, we had some changes to make. In the UK, before we came to the Netherlands, we had to actually change our props because, as I said in the first presentation, we didn't have enough thrust from our smaller props. So we had to change that. This pushed us outside of the size constraints set by the ESA, which means that in the Netherlands we had to trim our props as well as change some of the structure of the cannon in order to make it fit more perfectly, and in the end it did, which was good. We also had to create an electric fence using our GPS so that our directed landing wouldn't leave the military site and cause any danger. We created the square here, and we input the specific corner boundaries into the program so that it would cut off if it ever crossed and just basically drop out of the sky.
We had some problems with the bigger props because they had bigger holes in them than our original props, so we had to actually glue the props to the prop shaft using hot glue. During testing, when we tested at 100% throttle, the props would just fly off, so as a result, during the actual launch, we had to set the throttle for the props at 50%. So to compensate for this, we had to use a small parachute, which we also used to pull out a pin to tell the Arduino that it had been deployed from the rocket. So as you can see in this video, when we pull the pin on the parachute, the props will begin spinning, and of course the booms will deploy.
So if we look at the results from our primary mission, when it came to the actual thing, we lost radio signal with our can by the time it reached the launch site. So all this data is from the journey of it at our holding station to the actual rocket. So if we have a look at the pressure, it's pretty much consistent apart from one anomaly, which is what we expected. And if we have a look at a higher resolution of it, this has the anomaly removed. But you can see that it fluctuates a bit, but it's at such a high resolution that it didn't really make a big difference to our final reading. Then if we look at the altitude, again, it mirrors the pressure with the same anomaly. And then if we look at the higher resolution with the anomaly removed, again, it's a mirror, and the resolution means that this fluctuation doesn't make such a big difference in the long run. And then for our temperature, again, fluctuating, but with the resolution, this is all within 0.2 or even smaller. So our instruments work really well, and we're happy with how they went, and it's a reasonable temperature for the day.
Just a reminder of our secondary mission, which was to have our can using GPS guide itself to a target zone whilst sending data to us.
Right, well, as Louis mentioned, we had radio problems, and we've come up with a kind of explanation as to why that might have happened. As other teams had problems with the weather on that particular rocket, they were struggling to get radio signal. However, they were running at a baud rate of around 9,600. We were running at a much higher baud rate, and so loss of signal due to the weather would have been a lot more, it would have meant that it would transmit any data correctly. There was lots of data due to this. But as far as we can tell, the can did do its job, as Pranav will now tell you.
Yeah, so if we look at the landing, the can landed fine. There was no structural deformities or problems. Nothing had broken. The props were still on. In fact, I don't think we sustained any damage in comparison to the other team who our parachute tangled up with, which is interesting. Additionally, I asked the military personnel who brought the cans, and I asked if he could point in the direction of where he picked up the cans. Our two cans, our team which angled with, was slightly southeast of the other cans from the direction he was pointing. So this would imply that the software actually worked, the GPS software worked, and we had some movement. It's possible to say that if the other can hadn't been tangled, we could have moved further, but that's so we can't confirm that. If we're looking closely, everything's intact, all the booms are on, and the magnets have worked.
When the can was on the ground, we couldn't actually get a GPS fix due to the cloud cover. So we didn't actually get any GPS data at all throughout the day. But here's some GPS data from an early test of it sitting in the same location. And we can see that GPS fix, when it's got the fix, remains fairly constant. And if you convert the standard deviation in terms of degrees to a distance in meters, when taking into account the Earth as a perfect sphere, you get a distance of standard deviation of 2.5 meters, which agrees with the spec for the GPS, and is as good as you can get on a civilian GPS.
So here we have a video of us PID testing the can. This is done last night, once we got it back, just to test how the electronics have survived. So if you look at the middle three things on the computer, as we change the rotation, the pitch, your roll, the order of the sliders is your pitch roll. They vary, and so that's just like a visual representation of the data that we would then plug into our PID algorithm to help us navigate our can.
Unfortunately, we weren't able to actually we didn't get a video, we realise now, of the PID working on the can, and because the USB port snapped off on T- port, we can't actually program it, and it's currently running a test sketch, so we can't demonstrate a video of PID on the can, but here's a video on the larger quadricopter that we developed the software on, which is the same software as was running on the can, so you can see the PID algorithm working. You can see it damping any perturbation, brings it back to level, and then damps the oscillation the proportional term creates quite effectively. That's a much greater perturbation than you could ever expect. And then if I use I can control the angle it's trying to achieve, you get a slight stop-start motion. That's as the integral term fights against the derivative term in order to counteract the steady-state error that's created. But that's a demonstration of the PID algorithm working.
Okay, so where do we go from here? Well, we hope to obviously take the analysis we've got and put it into a final design and document, and hopefully put it in some forms of journal or some sort of publication, which would be great. We'd also love to help out in the UK domestic competition, which is happening for the first time this year, which would be great. We could help people understand what cancer that is and what sort of problems or maybe what you're going to get involved in if you do get involved in the competition. In terms of continuing outreach, obviously we'll keep with YouTube, Twitter, Tumblr, and Facebook, trying to make sure that everyone knows as much about the project as possible, as well as how it went, and the successes and failures. In terms of another big point, we're going to use the large quadricopter to lift our smaller quadricopter up and then drop test it so that we can test the effectiveness of the PID algorithm. So yeah, we're using a quadricopter to test another quadricopter.
So it's pretty important that we look at what came from this test and decide what we should improve for the future. Because we got no signal, one of the main things that we want to improve on is having onboard memory. We had none in the actual thing. So if we had some kind of SD card, once we recovered our can, we could have got the data and known something about our flight. We didn't have any problem with the electronics and the rain and the actual thing, but that was because we had to have kind of an emergency session of wrapping all our electronics in cling film. So we'd like to have a more permanent and proper waterproofing mechanism. And also a micro-switch on the bottom of the can so that we can tell once we hit the ground and then turn our motors off so that the propellers don't mash up with the earth.
We'd also likely not use the Arduino software platform because there are a number of inconsistencies we discovered bugs with the way it deals with C++ libraries that led to issues that were contrary to what the documentation stated. And that also, if we use a different chip, be able to make use of multi-threading in order to run the sensor fusion algorithm parallel to the PID algorithms, which would give better performance.
Okay, other considerations in terms of the structure of the can itself, we'd probably want to add some plastic screw threads because they reduce vibrations and also stop the boom from sort of pushing straight, like well past 90 degrees. If we want it to stay at 90 perpendicular to the can. Additionally, we'd probably want to integrate the wiring system a bit better and use some stronger hinges if possible. Maybe we'll look into a different material. Another important thing is the magnetic locking system. I don't know if anyone's seen that, but basically that's what basically holds the can, the boom up at the hinge so that it doesn't go above or it doesn't fall back down. This is a very important part, obviously, of the quadruplet design. So we need to make sure that's well integrated.
And so on to what we learned from this. So some of us had experience in specific areas. The rest of us have learned from others and from online sources like forums. A lot of skills. Most of us, we understand the basic principles of our program. We understand the mechanics and the mathematics of the quadricopter. We've had a lot of experience in trying to deal with difficult problems, trying to only use resources available to us at the time to solve them. We all helped out with the 3D design and then got experience with the hardware from 3D design, like laser cutting and printing, and then we all spent time trying to work out what our data meant.
Okay, thank you very much. Yeah, any questions?
In terms of your non-compliance with the width and I think the height before launch, did you know that was going to be a problem before you left the UK?
When we got the props, we knew it was going to be a problem when we left the UK, but we weren't able to do anything about it until we got to the Netherlands. And we were in some ways hoping that there'd be some tolerance in the requirements to save us having to make those adjustments, but we managed to anyway, so.
In terms of the tolerance, yeah, we were hoping because purely, like I said, the directed landing aspect of it did prove some problematic in terms of fitting it directly into the specification. So we did try our best, and I think in the end we did get the width and height into the limitations that were set by you guys in the night before. So yeah, I guess it worked out.
Yeah, about gluing the propellers on the axis. Sorry, this is a stupid never sticks to anything. You have other glues, like two-component glues that harden very fast. Why did you go for something like that? That might have.
In the final one that went up, we used super glue for it. We just didn't have any super glue at the time we were attaching the props. We used the hot glue because that's what we had.
And we'd like to say thank you to the Scottish team for providing us super glue at the last minute once our props had flown off yet again.
When we talked the day before launch, we as an organization applied a lot of rules on you guys. Eventually, you didn't use them, or you did use them. How did that affect the reliability of the software?
Yeah, so I think yeah, especially the electric fence that you guys placed on top of us, it did create a problem, but I think we actually had an idea that you were probably going to do that because it was a military range. So in terms of the way that RAF has designed the software, but it was very simple in terms of adding the. If you look at the screenshot, it was literally a few, either desired longitude max, latitude, and so forth.
It wasn't too much of a difficulty to integrate. The difficulty was more that we hadn't had a chance to test it, and given that it had essentially the power to drop the quad right from the sky, it was a bit unnerving having to put it in there, given that we had no idea exactly what it would do.
You mentioned that you didn't have the GPS fix on the ground side, and you mentioned that you think it's bad weather. I don't agree. Can you explain to me why you think that?
didn't find out exactly why it wasn't getting a GPS fix. We will carry out tests at some point in the near future to find out what the GPS was actually doing, whether it is actually a fault with the GPS, which I think is unlikely. I think more likely was its mounting position in the can wasn't ideal.
Yeah, to clarify, the main problem I think the weather caused was the radio communication problem. The GPS, yeah, could have been possible. We have to look into that side a bit more deeply. But we were more confident that the radio problem was caused by the weather.
In the case of the GPS fix, the software was programmed to imagine that it was at the launch, at the rocket position if it couldn't get a fix in order for the navigation. So even if it couldn't get a fix, we'd be able to demonstrate that it was navigating correctly. And so there was some redundancy programmed into it.
Now we have Aurora, Mr. Ford.